So, now we looked at 3 regions, right? Anode fault zone, cathode fault zone, and third one arc column. See, in that the anode fault zone and cathode fault zone, which are there just above both anode and cathode, very tiny, extremely tiny. If you make that bigger, these zones if they expand, then you have a serious problem on arc stability, because obviously if voltage changes dramatically, then you have a problem of energy gain, right. So, generally in a stable arc condition, the anode fault zone is very thin, 10⁻⁷ meters, extremely few microns. Okay. So, between the cold anode and hot arc column. Okay. And this region is characterized by the presence of electrons, the negative space carriers, energy carriers. And because this anode is positive, right. So, there you will not expect a positive ion sticking to the positive terminal because of repulsion. So, the anode fault zone is always characterized by the accumulation of negative space charges, the lack of positive ions. Okay. The voltage drop is somewhere between 1 to 10 volts. Again, if it goes more than that, then it is not sustained, right, and you have a problem again. And there is no thermal equilibrium, because if you want to have a thermal equilibrium, okay, so you need to have a collisions between the electrons and ions, which should be giving an equivalent energy transfer. Okay. Suppose if you do not have an adequate number of, in this case ions, so there will not be collision, adequate collision to make both ion temperature and electron temperature equal, is not it, because you have a large number of negative space carriers, charges, electrons. So, then electrons when collide, you will not get an equilibrium, because the ion temperature in this case will be much lower than the electron temperature, because there is no real equilibrium transfer. It's clear? So, there is no thermal equilibrium at this region, where because of the accumulation of electrons, the electron temperature will be much higher than the ion temperature in anode fault zone. Okay. So, that is what I have written here. The exchange of energy is incomplete, okay, because you are accumulating the electrons here, and due to that the electron temperature will be much higher. If any ion present in the vicinity, the ionic temperature will be much lower, because there is no energy exchange between the electrons, because you have only electrons. Yes, it is clear? Anode fault zone. The next fault zone is extremely important, the cathode fault zone, because the cathode acts as an electron emitter. Okay. If you do not emit electrons, there is no discharge, is not it. So, similar to the anode fault zone, cathode fault zone also is very tiny, 10⁻⁸ between the arc column and the cold cathode, whereas in here you have a positive accumulation of the accumulation of positive ions, which is negative terminal, right. So, you have surplus positive ions. The voltage drop is slightly higher than the anode fault zone, but it is about 10 to 15. Again, here also no thermal equilibrium, is not it, because you have only accumulation of ions. That means that the energy exchange is incomplete. But whereas in this case, the electron temperature will be much lower than the gas temperature. Okay. So, the gas temperature will be higher than, gas means here the ions, gas ions. The gas ion temperature will be higher than the electron temperature, because the energy exchange is not possible, because you have only accumulation of ions, is not it. the function of cathode is extremely important in welding case, because cathode emits electrons. So, if you do not emit electrons, how do you discharge? How do you discharge a gas atom? Because electrons first interact, knocks the other electron out from the gas atom, and you have a generation of positive ion, and that avalanche happens. So, the discharge is sustained. Okay. So, the main function of cathode is to emit electrons. Okay. It is very important. So, the function of cathode is extremely important, because that is where you emit electrons. So, once you emit, obviously it will travel to the electron will travel to the anode, but during this process it will also interact with the medium gas, causing some more emissions, the avalanche, the discharge. Okay. So, how do you emit? What are the mechanism behind the electron emission? By thermionic emissions. Okay. So, that is one type of emissions where you can emit electron from a material, thermionic emissions. Okay. That is good. So, how does thermionic emission work? You heat up, you heat electrode to high temperature. Okay. So, then the electrons are emitted, and that is determined by the work you need to emit or knock an electron out from a material. Okay. That is nothing but work function. Okay. So, the main mechanism behind the electron emission is thermionic emission, but thermionic emission alone will not give you the electrons. There is another emission, field emission. Okay. The field emission can also give the sustained electron emission, but both combined would generate electrons needed for discharge. Okay. So, in thermionic emission we heat up the cathode to higher temperature based on the work function, whether you emit an electron, or suppose if work function is very high. So, you need to increase the temperature much further. That is determined by this beautiful equation, Richardson-Dushman equation. It is not Dushman, it is a Dushman. Okay. So, Richardson-Dushman equation. So, where you see the current density or electron density emitted from a cathode is determined by, there are two important factors here, right? T, what is that? Temperature, and then this guy. Okay. E times 5. So, that is work function. Okay. So, this is the charge of an electron over potential difference, it is electron volt, EV. Okay. So, that is work function. So, if you multiply it by electron, which is nothing but the ampere, right, the electron density, the charge multiplied by volt, what does it mean? VI. VI means? VI means the energy, isn't it? Electron volt, that is a basic. So, that means that the work you do to emit an electron, okay, that is work function, isn't it? So, this is defined by EV, electron volt. Okay. So, that means that the work you should do to emit an electron from the material, okay, that is work function. And if you look at this equation and you have a T square, that is temperature, that means that when temperature increases, so obviously you emit more electrons, leading to increasing in current density, that means that electron density increases. Okay. And this guy, the E5 or EV, electron volt, it is a material parameter. Okay. How good the electrons are all bonded or in the the atomic configuration. So, generally material which has high melting point would also have a high work function. Okay. And if you want to have a thermionic emission, you need to increase the temperature to higher temperatures, then only you would have a thermionic emission, right. But now we have a problem, because if you want to keep an electrode, for example, if you want to make a non-consumable electrode, that electrode should have a high melting point, so that you can increase the temperature and then you can emit electrons, isn't it. So, now it is difficult. So, to emit an electron by thermionic emission, right. So, what do we do? We add some oxides. Okay. So, when we use a non-consumable electrode in welding, the material, the alloys would be having high melting point, but then if you have high melting point, you will also have a high work function. So, if you dope the material with high melting point with oxides, okay, so then we can promote thermionic emission. Yes. So, if you use a high melting alloy, most commonly used non-consumable electrode is tungsten. So, it is not pure tungsten when you do welding, we always dope with oxides. Okay. So, most commonly used the oxide dopant when I was doing my PhD was thorium oxide, but thorium oxide is radioactive. Okay. So, nowadays you can't buy thoriated tungsten electrode because it is banned, but that is fantastic. The electrode stability of thoriated electrode is very nice. Unfortunately, thorium oxide is radioactive, so it is replaced with cerium oxide. Okay. So, these are all rare earth oxides which have extremely low electron the work function. So, we dope the high melting alloys with these oxides, so that we can emit the electrons by thermionic emission. Okay. So, the equation defines the amount of electrons emitted as a function of temperature and the work function. You can use Richardson-Dushman equation to calculate. For example, if I give you a work function of a material and a material constant A, you can always calculate what will be the amount of electrons or density of electrons emitted by the material at a given temperature. Yes, you can calculate, right. So, if you dope it with oxides, the oxides have very low work function, which is beneficial. So, what do we do generally? So, if you look at the electron volts, so nickel has slightly higher electron volts than tungsten, but melting point is lower than tungsten. So, we can't use nickel as a non-consumable electrode, because it will melt by the time you induce a thermionic emission. So, if you use tungsten, the work function is reasonably okay, and you can heat it up to higher temperature, so that you can induce the thermionic emissions. That is why tungsten electrodes are commonly used as an electron source, okay, in SEM, okay, or cathode ray tubes, CRTs. Okay. When you have electron gun, tungsten is commonly used, right, because of this fact that high melting and electron volts, the work function is reasonably okay. So, you can work with tungsten to emit electrons. So, in order to increase the efficiency of thermionic emission, we also dope tungsten with oxides. So, oxides electron volt somewhere between 2 to 3 electron volt. Suppose if you have a tungsten electrode and you dope it with oxide, so obviously whenever there is an oxide and if a temperature is increased, this oxide would start emitting electrons by thermionic emissions, and because of that there will be electron emission locally in the oxides, and they can travel to the tungsten obviously then locally, and they would knock out further electrons from the tungsten orbitals, and then you will have a sustained emission of electrons from the cathode, right. So, the most commonly used the oxide dopant for tungsten is thorium oxide, and nowadays we also use cerium oxide dopants, and we will look at in detail when we look at the gas tungsten arc welding in chapter 2, what are the oxides, what are the functions of the oxides. Right now we can assume that the work function is extremely important. So, thermionic emission happens because of the high temperature. When you heat it up, obviously electrons go out. When you supply energy equal to the work function, the electron can be knocked out, right. It's clear, and we need to have reasonably high temperature. Therefore, we use high temperature melting alloys, where we have a doping of oxide leading to an efficient thermionic emission, because of the oxides have a low work function. It's clear? Okay. So, the thermionic emission alone cannot give sustained electron emission needed for the arc discharge. Okay. For example, if you use consumable welding process, not tungsten, you use say steel filler, you want to strike an arc, you can't expect a thermionic emission from a steel wire, isn't it? Then how do we sustain the electron emission? So, you need to use a field emission as your main source. For example, low melting alloys for steels, and you want to do a GMAW, gas metal arc welding. So, then if you make one of them cathode, either your steel wire or a steel substrate, so obviously you need to generate electron, right, from the cathode, otherwise you can't strike an arc, you can't make a discharge. So, in that case thermionic emission may not be sufficient. So, the electron generation mechanism in that case is field emission. Okay. But the field emission, if you want to have, you need to have a very high current density, amperage. Okay. So, we ignite the arc by the high density current density, so that we can also cause a field emission. Yes, what were your questions? Yeah. So, the field emission is helpful when you want to use a low melting cathodes, because thermionic emission is not providing enough electrons needed for the discharge. Okay. The phenomena of field emission is extremely complex. It only happens because of the electron tunneling. Okay. But the principle behind it is the electrons are tunneled and then it comes out of the surface because of the high energy density. Okay. So, you maintain by the field emission. So, you do not need a high melting alloy, but you need to have very high electric field to promote the field emission. Yes, it is clear. So, the function of cathode is to emit electrons. The cathode emits electrons by two ways. So, one is thermionic emission, the other one is field emission. Okay. The thermionic emission happens when you heat up a material to higher temperature, and if the energy, the heat is sufficient to knock an electron based on its work function, then the electron will be emitted from the material. Okay. The amount of electrons emitted by thermal emission, it can be calculated using Richardson-Duesman equation as a function of temperature, because all other things are constant in that equation, right. Okay. The work function is constant, material constant, only variable there is the temperature. With the temperature you can calculate, so what will be the current density of your electrons, right. So, second phenomena which also enhances the electron emission is field emission. So, field emission is widely used, or field emission is the rate controlling when you have a low melting cathodes. Okay. So, low melting cathodes also needs high electric field to emit electrons by field emission, right. So, the field emission governs the electron emissions in the low melting cathodes. It's clear? Okay. So, the two fault zones we have seen now. Anode fault zone, anode is mostly dormant. Okay. So, anode function is to have a cause a potential difference to charge carriers, so that charge carriers can travel. But the cathode determines the density of charge carriers. Okay. The cathode emits electrons. So, if you want to sustain the arc, that means that you need to supply the charge carrier, right. If you switch off the power source, what happens? You also stop the charge carriers, right. So, then there won't be any more thermionic emissions. So, when you pass an electron, obviously the electrode is also heats up by resistance heating, the temperature increases. Yes, it's clear. So, two emissions. Okay. So, now we will go to the important zone, okay, arc column, right. So, with whatever happens in arc column determines the heat generation, right. It's clear. So, it's beautiful, the arc column, right. It's very bright. So, what will be the temperature of this guy, the bright region? More than 10,000. How more than 10,000? Yeah, how much more than 10,000? 5,000 more than 10,000? Yeah, you are thereabout, yes. Yeah, the temperature is thereabout 20,000 Kelvin. So, the temperature of the arc, if I will show you in subsequent slides, at the central arc column will be close to 20,000 Kelvin. Okay. But unfortunately, we do not transfer the heat efficiently, because the conduction convection radiation is not that efficient. So, therefore, the process is not that efficient. If you can transfer the entire heat of the arc toward the arc piece, okay, so there is nothing like that. I mean, you will have a fantastic, you can penetrate 30, 40 mm plate even with 100 amperes current, right. So, the efficiency is not there, but arc is fantastic. We will look at it in what is happening inside. How does the temperature increase as high as 20,000 Kelvin inside the arc? Okay. Before that we will see again. So, if you look at it inside the arc, obviously there are two particles, fundamental particles. What are they? Electrons and ions, that is it. Okay. So, you will have electrons and ions. Of course, you will also have unionized gas atoms, or if you use diatomic gas, what are diatomic gases? N2, H2, CO2, diatomic gas. You will also have molecules. Okay. So, that is what the fundamental particles are, electrons and ions, and with that we can generate temperatures as high as 20,000 Kelvin. Okay. So, if you look at the arc column, it mainly consists of, as I said, neutral particles, neutral atoms which are not, which are yet to be ionized, or neutral molecules yet to be dissociated. Okay. So, if you have N2, you will have N2, but N2 will become N, okay, and then N becomes N plus, N plus further becomes N2 plus, N3 plus, until you strip off all the electrons. Okay. And if you have argon, argon becomes argon plus, and you generate electrons. Okay. So, the arc consists of two fundamental particles. Okay. Of course, if you consider the light is also a fundamental particle, you also have photons, but in our case we can assume the two fundamental particles, electrons and ions. Okay. So, obviously the electrons are negative ions. Okay. So, generally it is negative particles, sometimes you may also have negative ions. Okay. So, all the negatively charged particles would move towards anode, which is positive terminal. The positive ions would move to cathode, and during this process they will not go just like that. Okay, so when you are walking in the corridor, you do not collide with someone else, then you transfer energy. The other person either fall or you fall, because the other person can also transfer energy to you. Okay, so then you dissipate energy by falling down. Okay, so that can be pain as well. Okay, but in this case, so when the electrons and ion travel from cathode and anode, they also collide. Okay, so the collision obviously then discharge energy, right. So this collision can be the elastic collision and inelastic collision, and we can look at lovely mechanism behind these collisions, but we are not going to that detail because it is too much high temperature physics. We will assume now that the ions and electrons in the arc column, when they travel towards anode and cathode, they collide each other and they transfer energy, they dissipate energy. That energy is released as a heat, radiation, and various other mechanisms. So the heat is generated because of the collision when they travel from one end to other end. Okay. And if you have equal amount of electrons and ions, so then arc column becomes electrically neutral, right. So then the charge is neutralized. In most of the cases, if you have just arc, okay, arc is selectively electronegative because you always have more number of electrons than ions. Okay, always electronegative. But when the number density or the charge density of electrons and ions equal, then your arc column becomes electrically neutral. That state is known as plasma. Okay. So plasma is a state of matter, right. When do you call arc a plasma? Yeah, so when arc column becomes electrically neutral, then you call that plasma. Plasma is a matter, isn't it? So plasma is a matter because it is electrically neutral. Okay. So at a given unit of volume, okay, if you have equal number of positive and negative charges, then it becomes electrically neutral. When you have arc column electrically neutral, then you attain a state plasma. So if you want to do that, then you will have to do a lot of things. In a conventional arc, generally it is not electrically neutral. I have written this arc column is electrically neutral. So when you have a given unit of volume, you have equal number density of electrons and ions. Then you reach electrical neutrality and system becomes electrically neutral and you reach plasma state. Okay. So generation of plasma is extremely difficult. Given if you can strike an arc, okay, to create a plasma you need to do a lot of things. We will see when you look at plasma welding how arc changes into plasma. So as of now we assume that when arc column becomes electrically neutral when you have equal number of electrons and ions, but generally arc column is electronegative, you have more amount of electrons, right. So if you look at temperature in anode fall zone, what happens? You have accumulation of electrons, okay, then the electron temperature is much higher. In cathode fall zone, ion temperature will be higher, whereas in arc column you have thermal equilibrium because the number density is more or less equal. So the temperature of electrons and the gas ions would be more or less the same. Okay. And apart from electrical neutrality, you will also have a thermal equilibrium. Okay. And in arc column, because of the equal number density, there will be mutual collisions and then there will be complete exchange of energy between different particles. Ultimately, all the particles inside the arc column will have the same kinetic energy, isn't it? So, if you look at half mv square kinetic energy equation, and if you calculate all the particles kinetic energy, it will be equal, because there will be absolute mutual collision resulting in complete exchange of energy, right, and that is equal to 3 by 2 kT. What is K here? Good. Wind up here. Thank you.